and get started for the day. I'm going to start the day, as always, by looking at our checklist to see what you should have gotten done yesterday and what we got to get done today. Okay, so Tuesday, we are going to go over some questions. We're going to take a look at phosphorus, sulfur, and the water cycle with some review questions. And then I will go over TQ 1.6 and 1.7 that you hopefully completed last night. And some of y'all got pretty lucky. A couple of you guys sent me messages about some technical difficulties that you may have had on Friday and Thursday. And so for yesterday, I did reopen 1.4 and 1.5, but just for the day. In the future, if you have any issues, let me know immediately, right? So if you're trying to get one of these TQs, it's not working, and something's not working correctly with AP Classroom, send me a message as soon as possible, not a couple days later, so we can actually get it addressed when it needs to be addressed. And then we have our PowerPoint, our lesson for the day. We're going to be talking about primary productivity. And then you'll have a short reading, 2 pages tonight on primary productivity, which I would strongly suggest you read this because it is really important. And it's something that we're going to be talking about throughout the rest of the semester. And then you have TQ 1.8. I think it's 3 or 4 questions about productivity. Those are due tonight. Let me remind you guys that you do have your first biogeochemical cycle quiz, your first quiz tomorrow. It is in AP Classroom. It will automatically open up and it'll automatically close at 11:45 p.m. tomorrow. Now, as far as studying is concerned, I told you I don't do study guides. That's what these warm-up questions that we do every day are. And I would strongly encourage a lot of you, if you have not already, to go into your library and to look at the biogeochemical cycle reading. It's a PDF. And it talks about all of them, okay? And so it's a good synopsis of all the cycles, and there's unique diagrams that were not present in my PowerPoints, were not ones that we directly went over, but still kind of represent the various processes and cycles, little microcycles that may exist inside of each cycle. I think the quiz is 33 multiple choice questions, and a lot of them you'll actually have seen before, right? But there'll be some new ones included in there as well. It is open note. But remember, the more you rely on your notes, the more you rely on the internet, the more you rely on each other, the worse off you'll be when we return to a seated situation, because the biogeochemical cycles and our discussion of ecosystems, they are literally the foundation of every single discussion we will have from this day forward. So it'd be really, really rough to not fully conceptualize and understand these things. All right. And so, yeah, let's go ahead and take a look at the warm-up questions. I'll give you guys about 5 minutes to look at these, and then we'll go over them. Let me start my timer. So I'm a terrible judge of time, so I literally have to time out 5 minutes. Otherwise, I'd start too early because I get excited. Okay. I'm gonna sit here and drink my tea. Okay, about 2 minutes. All right. And I would like a little bit more voluntary interaction from y'all. As I had said, eventually we'll get to the point where I'll just be kind of randomly calling names off the roster for these answers as a way to keep you guys engaged. You know, my first period has done a fantastic job of involving themselves. You know, I have about 10 different people that are answering questions back and forth. And I really, truly think that it's going to have a long lasting effect on their performance. You know, this is not a television show. You don't just sit back and put your feet up. This is supposed to be, you know, an engaged interaction as best as we can while we're online. Number one, can someone tell me why is phosphorus a limiting factor for population growth in so many ecosystems and biomes? And there's more than one answer for this. So could someone share? Okay, so far I'm getting two good answers, right? So Elias said it's because it's slightly insoluble in water. And that's absolutely one of the major reasons why phosphorus is a limiting factor, because most of it is trapped in rocks. And it takes so long for it to weather chemically and even physically out of rocks to become available to the plants and their surrounding ecosystems. And then Ms. Gregg is talking about the rate or slowness of the process, right? So most phosphorus is trapped in sedimentary rocks or in the geosphere, and everything that happens uh, that's you know some kind of geological activity or geological process is measured in geological time, right? We measure time in minutes, hours, days, weeks, years, decades, centuries. And that's not how we measure geological processes. They take far too long. We discuss things in geology, it's usually hundreds of thousands, millions, or even billions of years, right? So the geological nature, right, or the fact that a lot of the phosphorus cycle does involve the geosphere makes it slow. And then Mary, you know, absolutely. There's no gaseous stage. There's no gaseous state of phosphorus. And so the phosphorus cycle tends to be regional, not global. So there is a significant uneven distribution of phosphorus on planet Earth. There's areas where there's a tremendous amount of phosphorus and then areas where there's very little. And since there's no gaseous state or no real complex atmospheric interaction that involves phosphorus, there's no way for it to be easily globally distributed. All right, let's look at number two. Well, actually, I already gave this away. Where are we going to find most of the phosphorus on planet Earth? Yes, it's going to be in the geosphere, right? In sediments and in sedimentary rocks. Okay. And usually phosphorus exists as a phosphate polyatomic ion in nature. Number three, what are some anthropogenic, and if you look at this word, anthropo is from anthropology. And if you study anthropology, you study human cultures and civilizations, right? So the second part of this, genic, is like to generate, or genesis means to create. So this is a human created or human synthesized issue, right? So it relates to humans. So what are some human related issues with the phosphorus cycle? Can anyone offer some ways in which we have change the phosphorus cycle? Yes, we do. We make a lot of fertilizers, right? Because phosphorus tends to be the number one limiting factor, right? We have observed in nature that soils with lots of phosphorus, plants grow fast. Plants in phosphorus poor soil don't grow fast. So, historically, we'd use things like bone meal, right? So people would take the bones from a butcher, they'd dry them, grind them up into a powder, and spread that in the fields to add phosphorus. Well, we've also figured out how to, um, mine it out of the earth and to create chemical fertilizers. So as these fertilizers get spread on crops, absolutely, Madison, right? Absolutely, right? So we spread phosphorus on these fields as fertilizers, but a lot of it gets washed away with runoff, and runoff is going to eventually end up in a stream or a river, which is going to go to a lake, pond, or an ocean, and could potentially cause what are known as dead zones. And Mary, yeah, that's how those dead zones form. It's through a process known as cultural eutrophication. So what ends up happening is this excess phosphorus ends up in these aquatic bodies of water, and the aquatic producers, right, the phytoplankton and the algae, they're also needing phosphorus, and phosphorus also is a limiting factor in their environments. And now you have this overabundance of phosphorus, and so the algae and the phytoplankton, their populations explode, right? They have all this access to phosphorus, so they're able to grow, they're able to reproduce, and the population gets really big. Well, we tend to only spread fertilizers seasonally, right? So you have this seasonal influx of phosphorus, and it's not continuous. So eventually, this abundance of phosphorus decreases, and now you've got this massive algal population without enough phosphorus. They will die and they sink to the bottom, and then they'll begin to decompose. The bacteria that will decompose these dead marine algae or freshwater phytoplankton, they need oxygen to do this. And so they consume a lot of the dissolved oxygen, a lot of the oxygen in the water, and that does not leave enough for the organisms that live in that ecosystem. And so we call them dead zones because a lot of the marine organisms or the freshwater organisms that live in the benthic zone near the bottom will die, right? And so we'll see thousands of fish wash up along the coast of the Gulf of Mexico, or fish rising to the surface in ponds and lakes that have that nasty green coat across the top. Brady, you're absolutely right. Sewage can actually contain a tremendous amount of phosphorus, right? So if any of that phosphorus ends up in the environment, whether it's in the ground, on the ground, or in a nearby body of water, that can contribute to eutrophication, like sewage if it gets in the water. And you can end up with incredibly high concentrations of phosphorus in terrestrial ecosystems that you might not have wanted it to be in, right? And so you could have an abundance of problematic plants like weeds or kudzu that have, kind of capitalized on this abundance of phosphorus. And then, yeah, we mine it up, right? So Troy was talking about digging up the phosphorus, right? And so when you dig up the phosphorus, you're not going to gather all of it. There's still going to be some remaining in that mining site. And so anytime it rains, some of that can wash away as well and cause problems. Not to mention, as we run out of phosphorus or readily available phosphorus for fertilizers, the cost of food will significantly increase as well. Let's look at number 4. When sulfur-containing gases, such as SOx, and remember that X is like a variable, you can put really any number in here, but usually in nature, sulfur forms sulfur dioxide, which would be a 2 right there, or sulfur trioxide, so that'd be a 3. So it could be either of those, or hydrogen sulfide, right? It smells like rotten eggs. If either of these gaseous forms of sulfur mix with atmospheric water vapor, what could be formed in the atmosphere? Yes, sulfuric acid, which could fall as acid rain if we're talking about wet acid deposition, or it could fall as a solid in what is known as dry acid deposition, right? And so both of those involve the deposition of sulfuric acid, whether it be liquid or in its solid state. All right. Next question. And we'll talk about why acid rain and this acid deposition is so problematic as we continue through our discussions. 5, what important geological resources contain sulfur and pose a potential risk of increasing both atmospheric as well as hydrospheric sulfuric or sulfur concentrations? So what are some geological resources that we have to dig up? Yes, fossil fuels are definitely one of these geological resources. Whether we're talking about petroleum oil, natural gas, or coal, there's going to be a sulfur component to those. And so by mining them, we can actually bring the sulfur to the surface, and then through runoff and erosion, it can contaminate nearby bodies of water. But when we burn and refine fossil fuels, right? So petroleum oil needs to go through a refinery plant before it can be used, and there'll be some sulfur released then. Same with natural gas. Now, coal, substantial concentration of sulfur, when we burn it through combustion in these coal burning power plants, they release sulfur into the atmosphere, and that can significantly increase atmospheric as well as hydrospheric. What else do we need to dig up out of the earth that tends to associate itself with high concentrations of sulfur? Mining for what? We already talked about the fossil fuels. What else? What else is valuable? Yes, yes, yes. Valuable metals like gold, silver, platinum, iron, copper, cadmium, zinc. All of these things. A lot of them tend to form ores, right? Or associations with other minerals or associations with sulfur. So a lot of our precious metals are bound in nature to sulfides, right? Or sulfur. And when we bring those ores to the surface, we need to smelt them, right? Which is a specific type of melting that removes the metal, the precious metal from the ore. And a lot of times the sulfur will escape as a gas into the atmosphere. So smelting of precious metals and the mining of precious metals can bring sulfur deep beneath the earth to the surface. So you're realizing now that, yeah, a majority of the sulfur on planet Earth is in the ground, right? Now, what is a natural way that a substantial amount of sulfur can enter the atmosphere? Or actually, no, correction. Drop that question. Where on Earth could we find purer forms of sulfur? And remember, sulfur tends to be yellow, right? And so where could we find pure forms of sulfur in nature? Yes, volcanoes, right? And so when you get closer to volcanoes, especially if you get really close to any of the vents, right? You're going to find this like yellow powder, or you're going to find clumps of sulfur in the soil, right? Because these volcanoes are emitting hydrogen sulfide gas. And as that gas cools off, right, it can precipitate or solidify as a solid. In Yellowstone, you can find lots of sulfur. In fact, there's a creek in Yellowstone National Park that I've visited and collected some samples of archaea from, called Lemonade Creek. And the reason it's called Lemonade Creek is because this hot water is bubbling up out of an opening and flowing as a creek, and it's got so much sulfur in it that as some of the water evaporates on the stream bank, it leaves behind this yellow powder, and it's almost pure sulfur in it. You can tell because it smells a lot like rotten eggs. So volcanoes and any kind of volcanic activity is going to produce sulfur. Let's see here. And then, there's also things like fool's gold, which is it's pyrite. So it's like iron and sulfur together, that can appear to be like metals, but simply just a form of sulfur and other metal. Number 6, runoff can contain abnormally high concentrations of both phosphorus and sulfur. What zone or area around a river can reduce the amount of phosphorus and sulfur contaminating that particular body of water? What do we call that? Yes, Madison. It's called riparian zone. And how, yeah, you're there, man. It acts as a buffer. And so we call this specific buffer, we call it a riparian zone. So along streams and rivers, there are plants that are actually very special. They've got a lot of adaptations, right? They can deal with, having roots in saturated soils, and they assimilate nutrients really well. And it's incredible in the way in which they can actually protect these bodies of water from being contaminated by high concentrations of nitrogen and phosphorus and sulfur. These plants readily assimilate these nutrients because they need them and prevent them from getting into the aquatic ecosystems. So that's why the vegetation, right, the plants and everything along streams and rivers, they're really important. not only do they biologically assimilate these nutrients, they act as a physical barrier, right? So when you studied runoff in middle school and elementary school, or when you're outside exploring the world, we've all seen how water flows across a bare hill, right? Where there's no grass, it's just dirt. The water creates these really rough furrows and it flows really quickly, right? And we've seen the same hill with grass on it. And we notice that as the water flows over the grass, it slows down a little bit. There's like some physical barriers there. If you have grass and shrubs, the water moves a little slower. Grass, shrubs, and trees, again, a little slower. Those plants act as physical barriers, right? And so they're going to increase the rate of infiltration versus runoff, right? So runoff and infiltration, they're kind of like opposite ends of the spectrum. Runoff happens when water doesn't have a chance to sink into the soil. Infiltration happens when the water doesn't have a chance to move, right? So the more vegetation we have on a slope, the more infiltration we'll have, right? And so the riparian zones, since riverbanks are usually sloped, act as a wonderful way to reduce runoff and increase infiltration. Number 7, and there's like a bazillion answers for this, but I just want to kind of start this conversation. In what ways does the hydrologic cycle benefit human populations? And I just want to go ahead and jump on somebody who just posted a list to power our homes, right? Water loves to flow from high elevation to low elevation, forming rivers, right? Well, how does the water get to the top of the mountain first, right? Where does this water come from that feeds these rivers? And that's going to be precipitation, right? So this distribution of water, this uneven distribution of water creates this flow, right? From high elevation to low elevation. And we can use that. We can harness that to produce electricity. Yes, we all need it to drink, right? And we can use it to irrigate our crops. Yes, the hydrologic cycle is definitely an important part of that distribution, right? Because there's places in planet Earth where there's lots of water and places there's not. And the hydrologic cycle can sometimes distribute the water, but it'll never be even, right? Now, when we talk about drinking water, right, we know that majority of the water on planet Earth is salt water in the oceans. And we all know that most, if not all, rivers and streams in one way, shape, or form flow towards the ocean. And the same can be said about groundwater, right? Unless we're talking about fossil water, we'll talk about that later. So if all the water is trying to get to the ocean, why haven't all the rivers and streams dried up? Why haven't all the groundwater aquifers dried up? Why is all of the water on planet Earth not in the ocean? How does water get from the ocean back onto land?
The water cycle.
What happens in the water cycle? How does the water get from the ocean back on land? But before it can fall as precipitation.
Condensation.
Before condensation, right? Because that's the condense into a cloud to, yes, evaporation, right? And the amazing thing about evaporation, and you may or may not realize this, is if you were stranded at sea, you can't drink the ocean water, it'd kill you. But if that same water evaporates, condenses above your head in a cloud and falls as rain, you can drink it. And that's because evaporation is nature's form of distillation. And distillation is a process that utilizes the various boiling points of different liquids. So when water evaporates, it leaves behind a lot of the salts. It leaves behind a lot of the dissolved solids and then condenses in the atmosphere as a more fresh form of water, right? The salinity has significantly decreased, and prevailing air masses can push these clouds well inland to fall as precipitation, okay? So evaporation is like nature's distillation. Now, you can also get your drinking water from a well, and wells tap into groundwater. Why do we like and why do we utilize groundwater for drinking rather than just grabbing water out of a stream or a lake? As water enters soil, what two processes allow water to enter soil to eventually become a part of groundwater? Infiltration and percolation. In Madison, that's exactly what both of those things do, right? So as water infiltrates the soil and then eventually percolates down through semi-permeable or permeable forms of rock, the water is physically filtered. right? Any large dissolved solids get removed and the water continues. And there's also some chemical components to soil that can chemically filter water. So that's why by the time the water gets down into the aquifers, it's much safer to drink. So you've got natural distillation, right, through evaporation, condensation, and precipitation. And you've got natural filtration through infiltration and percolation. There are many more that we'll talk about later on, but I want to go ahead and jump over to our, I didn't mean to stop sharing. So go ahead and jump over to our TQs from last night so I can quickly talk about those with you guys. So got TQ6 first. Phosphorus in aquatic ecosystems, right? So you got a diagram right here. Which of these is the best explanation for why there's such a small amount of phosphorus that moves into the aquatic ecosystem? Well, first and foremost, it's slightly insoluble in water. Most of it's trapped in rocks. And since it's slightly insoluble in water, it takes forever for it to be released, to be weathered out of the rocks. And there's no gaseous component, right? So there's really no way for it to get from the rocks into the oceans easily, okay? So here we've got lots of other reservoirs, and you can see there's numbers. And don't forget how scientific notations work. If you have issues with this, please email me and I can help. But all you need to do is move the decimal to the right 8 times. So that's a massive number. We use scientific notation to easily write big numbers instead of writing out all the zeros. So the movement of phosphorus between biological organisms and soil tends to exist in an equilibrium or a steady state, if you will, in an undisturbed system. Which of the following best explains why this would be? And it's because plants need phosphorus. It's a limiting factor. So most plants are really well adapted. There's a lot of biological adaptations that allow them to readily absorb any available phosphorus in the soil. And as quickly as the plants absorb and assimilate the phosphorus, they will very quickly produce fruits, vegetables, flowers, and the like that are consumed by consumers. And that excess phosphorus will be excreted as a waste, or the plant matter will die, or an animal will die. And the decomposers are really good at getting phosphorus out of that detritus or that decomposing matter and back into the soil. So it's a very, very efficient system because there's so little of it. Based on the diagram, which of the following reservoirs contain the most phosphorus? According to this diagram, it would be sediments. But this diagram leaves out sedimentary rocks. And we all know that most sediments, through heat, pressure, and time, will eventually become sedimentary rocks. So sediments is the best answer here, but overall, you'd have way more phosphorus in sedimentary rocks. All right, let me go ahead and jump over to TQ 1.7. And shame on some of y'all for still not completing these. All right, so here we got 2 plots of vegetation. Used to be pasture, and now it's got some vegetation. So how is this going to affect the water cycle? Well, it's exactly like we were talking about earlier. The more vegetation you have, you're going to reduce runoff and you're going to increase infiltration. Because before, when it rained here, water probably pooled up and either washed to and fro. We had a lot of animals stomping on the ground, so they probably compacted the soil. And any water that fell on the surface, if it didn't immediately infiltrate the soil, if the sun came out, it would easily evaporate. Now with the vegetation here, when it does rain, you're going to have water reaching the surface more slowly, right? Because some of the water is going to hit the leaves and bounce back and forth before it eventually gets to the ground, which gives the water that does reach the soil time to infiltrate. And then if the sun does come back out later after a nice heavy rain, there's going to be more shade, and that's going to reduce evaporation and give water more time to infiltrate. So these trees, you'll be really happy, right? And it's kind of neat, because plants, every organism in one way, shape, or form modifies the environment around them. And plants do this substantially, especially when we talk about soil and soil structure, but we'll get to that later. So increased infiltration is the best answer. All right, so here we have water cycle. Which of these would be most affected by impervious surfaces? So if something is impervious, it's impermeable, like concrete, parking lots, asphalt, and the like. And that's going to affect runoff and infiltration, right? So D would be your best answer, right? So if you have concrete and asphalt right here, as the rain falls, and as any kind of precipitation, it's going to be way more likely to flow as runoff if there's asphalt or concrete, and far less likely to flow down through infiltration and percolation. So your best answer is D. And then which of these represents water going from a liquid to a gas? That'd be evaporation over here. Those weren't too hard. Let's go ahead and dive into our lesson for today. Don't forget, TQ 1.8 is tonight. So what I want to talk to you guys about today is something known as primary productivity. So primary productivity is the way in which we measure, right, the amount of energy transferred from the environment into the biosphere. Generally speaking, what we're looking at is photosynthesis, right? How well or how much energy do the plants, phytoplankton, algae, or photosynthetic bacteria, how much are they able to fix from their environment into a usable form of chemical energy? Now, this is photosynthesis, right? So plants are going to use the sun, carbon dioxide from the atmosphere, and water to produce carbohydrates or sugars. Now, the plant produces those sugars as a form of energy for itself because that plant needs to grow. I need to produce new leaves, new roots. It might need to synthesize new proteins. It might need to, kind of change its position to capture the sun. And some of that sugar is going to be used for cellular work. And we call this respiration, cellular respiration. So the plant not only is able to take carbon dioxide and water from the environment in the presence of sunlight and make sugar, it's also capable of taking those same sugars, breaking them down in the presence of oxygen to release energy and also carbon dioxide and water to the environment. Now, the plant is probably going to produce more sugar than it needs. And some of those sugars are going to be used to create biomass. They're going to be used to create proteins, fats, oils, waxes, which are known as lipids, DNA molecules, and even structural sugars. Plants, their structure, their cell walls are actually made of a type of sugar, right? And so some of that energy does get stored in what is known as their biomass. And so the biomass would be the weight of this plant without water. Okay, so when we measure biomass, it's like a dehydrated form of the organism. We would need to sacrifice this plant, dehydrate it, then weigh it. That would give us an accurate biomass because that would tell us, the mass of the organic compounds, right? Water is not an organic compound. It's H2O. It does not contain any carbon. Now, when we measure, right, the productivity or the rates of photosynthesis for ecosystems and plants, we call this total, this overall amount in a given area over a given year, gross primary productivity. So gross primary productivity can have a lot of different units. Sometimes it's referred to as grams of carbon per area per year. Sometimes it might be given in joules, which I'll get to in a second. It's a unit of energy. So it might be like, energy per area per year. And we can also be given in kilocalories or even calories, the way that we measure energy contents in food. But this would be the total amount produced by the plant, the total amount of sugar captured and stored by the plant. Let me say captured and made by the plant in a given area over a given year. But we need to figure out how much of that energy is actually available to the rest of the biosphere, right? So how much of this energy was fixed by the plant, but how much is really available to the consumers, the primary consumers and the secondary consumers? And to figure that number out, we have to remove or subtract the amount of sugar the plant needed to survive that year to figure out how much of that energy would actually be stored in that plant in a given year. And that gives us this equation right here. Gross primary productivity minus respiration equals net primary productivity. Net primary productivity would be the amount of energy or biomass available to the consumers. And you can think about this like income. I could tell you guys how much I make a year, and that would be my gross income. But I have to pay taxes, right? There's a certain amount of money that I need to pay immediately just for the infrastructure that I live and exist and teach in. And what I have left over will be my net income, right? That's what's available for me is like spending money, okay? And so gross primary productivity is how much sugar did the plant make in total? How much sugar did it need to use to survive? And then how much is left over? And the sugars that are left over are available for the consumers in that particular ecosystem. And these numbers vary greatly from one ecosystem to the next. Now, let me just give you a quick real example, or not quick real example, a quick easy example. Let's say we were studying one plant. And that plant produced 100 grams of sugar or glucose in 1 year. Okay. We could also monitor respiration. We could figure out how many grams of that sugar the plant needed to respire or to break down through cellular respiration to stay alive. And let's say it broke down 25 grams of the carbohydrate or the sugar through respiration to maintain homeostasis, right? So how much do we have left? Well, if it made 100 grams and it had to use 25, 75 of those grams of sugar will be stored in biomass each year. Okay. And so these 75 grams will be the 75 grams of biomass available to the consumer. So let's take a look at how this plays out around planet Earth. Well, so here you've got your plant capturing sunlight, water, and carbon dioxide, performs photosynthesis. And this would be like a measure of all of the energy captured, right? And that's a joule. That J stands for joule. And a joule is just a measurement of energy, right? So 300 units of energy. Well, that plant needs to use some of that energy to stay alive. And we always lose energy as heat, right? So 100 joules of that is lost as respiration or heat. And so really only 200 joules or 200 units of energy get stored in the plant biomass, right? And so this is our equation right here. You can kind of see it, right? This would be our GPP, right? And then we've got our respiration rate, and then here's our net primary productivity. And so hopefully it kind of makes sense now. You can take your gross primary productivity, which in this case was 300, and we subtracted respiration, and that gave us our net primary productivity, which was available to the consumers, right? And so these fruits and vegetables are maybe intended to be eaten for sexual reproductive purposes for plants or propagation purposes. And so this little caterpillar munches the biomass in this particular fruit. Well, this organism is not going to convert every single joule or every single calorie from its food into direct energy. And this animal is definitely not going to take every gram of its food and convert it straight into biomass. Let me give you an example. If I ate 15 pounds of cheeseburgers right now, would I be 15 pounds heavier tomorrow? And the answer is no, because I'm going to release some of that as urine. I'm going to release some of that as feces. My body's going to break a lot of it down for energy in the immediate, next couple hours. And every time I exhale, I'm losing weight via carbon dioxide. And then breaking it down takes energy. And these chemical reactions, we're going to lose a lot as heat. So although this little caterpillar, although he ate 200 joules worth of energy, some of that energy is going to go to digestion and he's going to poop some of it out, right? And we actually call the feces of insects frass. And then the organism needed to expend energy through digestion and through movement and through the mastication or chewing of the fruit. So it's going to lose some for cellular respiration as well. And so you can see at the end of the day, there's not a whole lot of energy that's going to be directly stored in the caterpillar. And this will be really important later on in our discussions of conservation. You can see it's a pretty inefficient system, the flow of energy from one organism to the next, even from the environment. You can look at gross primary productivity over a 16-day span in the United States of America. The light blues and greens are where we're going to have a lot of gross primary productivity, and the whites and browns where we don't have a lot. Now, if you look down here in the southeastern portion of the United States, what about the southeastern parts of our country allow for such high rates of gross primary productivity, right? This is kind of a measure of photosynthesis. Why are the plants so happy down here? Can anyone hypothesize as to why that might be? Nobody? Sunlight, soil, but more importantly, climate. Yes, moisture, rain, and temperature. Plants are happy down here because it's warm and it's wet, right? Plants like warmer environments and they need water for photosynthesis. There is good soil here because the Appalachian Mountains at one point were the tallest mountains, bigger than Mount Everest, and they have weathered and eroded over time, creating very nutrient, mineral-rich soils. But it's all about temperature and moisture here, right? And if you look at the months, March through April, right, this is spring, and it gets real warm and you get those those spring showers and the rain. So the plants are really happy here, right? Now, what about up here? You got Montana, North Dakota, and South Dakota. Why is the gross primary productivity so low here, right? This is the American prairie, right? Why is it so much lower? Yes, it's colder and drier. So if you look at this March, spring in North Dakota is still really cold. And these areas can actually be quite dry. That's why they're American prairies. It's like temperate grassland. Now, if we shoot straight down right here to West Texas and parts of New Mexico and Arizona and northern Mexico. Why is the primary productivity so low here, despite being on the same latitudinal plane as somewhere like Florida? Why is there so little photosynthesis there? Yes, it's dry, right? Yes, exactly. It's dry and it's much hotter, right? You know, the water around Florida actually regulates the temperature quite a bit. Whereas the further you are away from oceans, you get less of that thermal regulation. So you might have, scorching hot days in Florida in the low hundreds, upper 90s, but then you're going to have scorching hot days out here where it might be like 110, right? And that's not good for vegetation. And then if you look over here, you got a little pocket of really, really high primary productivity. This is actually a temperate rainforest, right? Up here in Northern California, coast of Oregon and Washington State. This is a temperate rainforest. So it's at moderate temperatures and heavy rainfall. You can also look at the distribution of gross primary productivity around the world, red being low productivity, purple being high productivity. And you can look along this central line and see that there is a concentration of productivity here, right? These are our tropical rainforests, and this line right here is the equator. So along the equator, we've got a lot of warm temperatures, right? 12 hours of daylight, 12 hours of darkness every single day of the year. That's why we call it the equator, right? Equidistance from the poles. And so they get a constant supply of sunlight and warmth, and there's lots of evaporation. So that lots of evaporation, you have lots of precipitation. If you look a little further north or a little further south, you have 30 degrees north and 30 degrees south. And along 30 degrees north, you find a lot of the world's deserts. And same with the 30 degrees south. In fact, this right here is the driest desert on planet Earth. This is Atacama, I believe it's called. The Atacama Desert is sandwiched between the Andes Mountains and the Pacific Ocean. It stretches all the way down from the southern portions of Peru down into Chile. This area is so dry, it is often used by NASA and other space agencies to test um, uh, Mars protocols, probes, because this is about as close to Mars as you can get on planet Earth. This place is dry. Some of the weather stations down there have no record of rainfall in their little small areas. And this desert in general gets somewhere between like 0.04 to half an inch of rain in a year. It's the driest place on planet Earth, right? And it's because of the way in which air moves from the equator or south, north or south. And we'll talk about how that plays out later when we discuss weather. And you can see there are some exceptions to the rule, right? Where you can see pockets of productivity, like up here, these coniferous forests, or down here in Sweden, right? You can see that Norway and Sweden's, their productivities are substantially different, although they're almost on the same latitudinal line. And a lot of that has to do with altitude, like you can see here in the Himalayan mountains, right? You can almost like look at mountains, right? You can see the little white spots popping up here and there. We can also look at this in the oceans, right? And so when we look at productivity in the oceans, we're not talking about plants anymore. We're talking about phytoplankton or algae. And you can see that the distribution of productivity around planet Earth is not equitable, right? It's not an even distribution of energy production on planet Earth in the oceans. You can see there's areas where the productivity is incredibly high, and then areas where it's incredibly low, right? Now, we all can kind of assume why the productivity down here is rather low, right? This is Antarctica right here. It's not this big. This is like a Mercator projection, so it's kind of stretched out to make it look flat. There's just really, really, really cold down here, and really low temperatures affect enzyme function. We'll talk a little bit more about that tomorrow. But in other parts where you would think, okay, this is probably as far away from the equator as this is, so why is the productivity higher up here? That's because of the Gulf Stream, right? So there's a movement, an ocean current that brings a lot of warm, nutrient-rich water from along the coast of North America and dissipates that heat energy up here. And as the water cools off, a lot of the nutrients precipitate out and support these marine fisheries. You can also see areas along the coast, that have high levels of productivity, right? How can anyone explain this little spot of red, this high productivity right here off the coast of South America? Why is there so much productivity here? Why are the phytoplankton doing so well? What's the number one limiting factor for all ecosystems, ladies and gentlemen? It is warm. Yes, phosphorus, nitrogen, nutrients, right? So why are there nutrients here and maybe not here? We know that phosphorus is generally held up in rocks, right? And so we need to have weathering and erosion. So what is going to deliver or distribute or transport phosphorus from weathering rocks to this particular location? What dumps out right here? Anyone know? This is like world geography, y'all. The most famous river on planet Earth. Oh no, I'm dying right now. Come on, please tell me. Biggest river, most famous river on planet Earth. Yes, thank you. The Amazon, it's a massive network of river systems, and it's going to be slowly weathering and eroding rocks and collecting nutrients, and it dumps it out here into the Atlantic. And you got other parts of it down here that dump out. Where you're seeing these red areas, a lot of times are river deltas, right? So it might be the Amazon, might be the Congo River right here. You can even see the river delta of the Nile. Oh, shoot. You can see the Nile right here. You can see the Gulf of Mexico. You can see the Colorado River. And so river deltas can deliver a lot of nutrients for these phytoplankton to thrive, right? And then some areas it's not rivers, right? Again, the Andes Mountains are right here, so there's not a lot of weathering and erosion, right? A lot of these areas are dry, like the Atacama Desert. Yet in the oceans, there's a lot of productivity, and the reason for this is known as upwelling. I talked a little bit about this yesterday. Deep ocean currents bring nutrient-rich water up to the surface, and you get these little upwelling events where you're having a lot of productivity. And so pretty much anywhere where you see these red and green areas, there are civilizations and cities and entire communities and cultures built around fishing because the productivity is so high in these areas. And these areas are not static. They do change, especially these upwelling events and even some of these river deltas, because ocean currents change. There's two things, El Nino and La Nina, that can significantly change the global distribution of temperatures in our oceans, but we'll talk more about that later. We can compare and contrast the net primary productivity, which would be the amount of energy or grams of carbon left over for the consumers. And you can see that in wetlands, right? Estuaries, swamps, and marshes, and estuaries especially have really, really high net primary productivities because there's a lot of nutrients available, right? And we tend to find these ecosystems in warm climates, right? So warm and wet, that's good to go for photosynthesis. And that's why you see tropical rainforests up here, right? So warm and wet is good for photosynthesis. But again, you have to have nutrients, right? If you look down here on the opposite end of the spectrum, you see that, the tundra, desert scrub, and extreme deserts, the limiting factor here for the productivity is water. Water is a essential reactant for photosynthesis. No water, no photosynthesis, right? Now, if you think about the open ocean, well, it's all water, right? And so why is the net primary productivity so much lower? And that's because if you're smack dab in the middle of the Atlantic and you were to take a surface sample of water, there's not going to be a lot of dissolved nutrients because when things die and decompose in the ocean, they tend to sink to the bottom. And so although there are phytoplankton out in the open ocean, their populations are limited. Their ability to perform photosynthesis are limited by the available nutrients, although it might be sunny and it might be warm on the surface. Continental shelves, right, like corals and seagrass beds and things like that, their net primary productivity is much higher than the open ocean. That's because the water is shallow, right? So you get more sunlight penetration. It's generally going to be warmer, but since it's close to continents, continental shelf, the proximity to land means there's going to be more runoff. There's going to be more deposition of nutrients from streams and rivers and from just terrestrial runoff in general. The last slide I want to show you guys is like a graphical comparison, right? Looking at two variables, two abiotic conditions and their effects on productivity. In this graph right here in the y-axis, we have dry biomass, right? So you could almost consider this like net primary productivity. It's measured in grams per square meter per year. And then you have the same y-axis on this graph. and we have two variables. We were looking at temperature and precipitation and how it affects productivity. And if you look at this graph, you can see that the highest rates, right, of productivity are occurring in warmer temperatures, right? That's not always the case, right? You can see that the productivity of these particular ecosystems were as high, if not lower, than these, right? And you can see that these plants are more well adapted for a cooler temperature and these plants for warmer temperature. In fact, this is probably a coniferous or boreal forest. Believe it or not, the productivity of coniferous and boreal forests is pretty high. The boreal and coniferous forests of like North America and parts of Russia produce a vast majority of the oxygen that we breathe. And this might be like a, a temperate ecosystem, perhaps. Now, if we look over here, we are looking at precipitation, the amount of rainfall. And you can see there's some extreme champions over here producing, a couple kilograms of dry biomass, right, in a given year. And we can see that they get a lot of rainfall, right? And if you reduce rainfall, you can see that you're substantially limiting the amount of biomass that can be generated. And this all has to do with enzymes, right? And I'm going to talk a great deal about this tomorrow, right? It's something that we talk a lot about in biology. It's like kind of a dogma of all discussions involving life. So make sure to go read that section 1.8 on productivity. Make sure to complete your 1.8 TQ questions for the night. If you have any questions about anything while you're reading or while you're working on your TQs or simply studying for your quiz tomorrow, please don't hesitate to ask. Okay, don't forget you do have a quiz tomorrow. It will close at 11:45 p.m. tomorrow night. I am available if you want to shoot me an email or remind today or tomorrow if you have questions about anything. But other than that, that's all I have for today. I do want to say one thing to y'all. We have got to improve y'all's participation, right? This is an AP level class. I will not tolerate and will not stand for a class of just silent observers, right? You're not going to do as well. I'm telling you right now, I've been doing this for about half as long as you've been alive on planet Earth. And the less questions you ask, the less answers you provide, the less engaged you are, the worse you're going to do. I mean, it's not rocket science. I can promise you this. Those of you that have answered questions, I can almost put you in a list and I can already predict that you're going to do better than everyone else. And so I am going to switch as of Thursday for y'all. I'm going to be randomly calling people on the list. All right. Because that was rough. All right. So let's try a little harder next time. All right. Well, I hope you guys have a wonderful day and let me know if you have any questions. Yeah, you too.